Software Engineering Daily is sponsored by Hired.com. If you're looking for a job, Hired.com is the place to start. I've used it personally and it is an excellent service. Software engineers and designers can get 5 interviews in a week with top companies. Go to hired.com/softwareengineeringdaily for a $4,000 bonus upon accepting a job. Thank you, Hired.com. Grant Ingersoll is CTO and a founder of Lucid Works, a technology company that builds search, machine learning, and big data products. Grant, welcome to Software Engineering Daily.
Jeff, great to be here. Thanks for having me.
What kinds of applications need search functionality?
Yeah, that's a great question, Jeff. It's really evolved quite a lot over the past few years. I think, 6, 7, 10 years ago when people thought about search, they just thought about keywords in a text box a la Google or Bing or Yahoo. And I think what, those of us who've been in the know with search have been evangelizing and showing the rest of the world is that the core algorithms and data structures of search really help drive and answer lots of other interesting questions. Because what they do, what search really brings to this table is this notion of ranking or of importance or of helping you figure out in your data what's important. And this is especially true in the case where you're mashing together lots of different data types and data sources, and you want to have come back up and out to your users something that's ranked according to how relevant you think that is to them. And I think as people have been building more and more data-driven applications, that notion of importance and of relevance is becoming, excuse the pun, all that more important. And so these applications where, going beyond just a search box, where you want to for instance, look at fraud, look at compliance, look at traditional e-commerce kinds of things, as well as just provide data to your users in a way that they can naturally interact with it, is really a great spot for search. It also, at the end of the day, because people are so trained on search, right? Because that's how we do everything these days, right? You go to Google, you go to Yelp, you ask Siri, you ask Google now. That search box and that way of just querying the data in a much more natural way than, typing SQL or any of those ways. It has put the search box and search, I think, front and center in a lot of applications that wouldn't traditionally have been search-based applications.
You've said that search is a system building block. What do you mean by that phrase?
Well, I think, what I was just talking about really gets at the core of that, right? Is that more and more, as you have more data, as you have more different types of data, you really need a way to prioritize that data for your users. And so it becomes a part of every application stack, just like a database, or what, in some cases, even you can replace the database with, search as that building block. I think the other thing that a lot of people don't realize about search is that it's actually really good at a lot of other traditional NoSQL or database use cases. So, for instance, if you think about key value and you think about ranking as a problem, right? So, search engine is optimized for bringing back top 10, top 20, top N items, right? So, that's kind of the traditional search case. Well, if you think about key value, in many ways, key value is just N equals 1, right? And so a search engine like Solr actually performs quite well as a key value. Is it as good as a purpose-built key value store? It kind of depends, but it may not be. But once you factor in that, in most key value cases I've seen, the very next thing you want after good key value is search over the values, aka secondary indexes. And so then what people start doing is they build these really complex systems where they're trying to keep 2 large-scale distributed systems in sync, like a Cassandra and a Solr, or a Mongo and a Solr, or fill in the blank and a search engine, right? And if they actually looked at their SLA requirements, they would realize that something like Solr would give them all they need on the key value side and give them the secondary values. And operationally, now they only have one distributed system they need to take care of instead of two. And so, I think that's a good key value case. Engines like Solr, Lucene, they have lots of spatial capabilities. They're quite good at numerical data as well. Actually, in upcoming release of Lucene and Solr, there's actually going to be full-on JDBC parallel SQL capabilities, such that you can do full SQL type operations on the search index across very large clusters and still have a real powerful working, fuzzy matcher, if you will.
So your company, LucidWorks, helps enterprises build search applications. And to get a better idea of this process, could you walk me through the prototypical example of a company that doesn't have search capability? Maybe they have a database with everything that's, everything in their company is just in this database, and they come to LucidWorks and they need help building out search functionality. What does that typical situation look like?
Yeah, so at LucidWorks, we primarily engage with customers on a couple of levels. The first level is we have a product called LucidWorks Fusion, which is built off of several key open source capabilities. The name Fusion kind of implies that, actually. So we're bringing together what we consider to be best in breed open source and packaging that up. And then on top of that, we add a lot of value add. So, essentially the company's built around an open core model for open source as a business. So with Fusion, you get data connectors, you get ETL tools, you get Solr, you get Spark, you get a bunch of other pieces. More importantly, though, what we try to do is short circuit a lot of the things that go into building an application by shipping reference implementations, by shipping good out of the box capabilities. And so what a customer typically is doing, and a lot of our customers actually have some version of search in-house already. They're either on a legacy proprietary system like a Fast or an Endeca or a Google search appliance or an Autonomy, or they've actually rolled their own in open source and have just kind of got stuck, which can happen. I mean, we've all been there on that one. And so what they usually are looking for, if they don't have any experience with search, they're often coming to us for just the kind of, hey, straight up, I know I need to put search into this application and kind of, the traditional search experience. But what usually happens somewhere along the way is they have this light bulb moment where they start to realize that search does all of those things I've been talking about, and that they can solve a lot of more interesting problems, right? So typically, our customers outside of e-commerce, I'll come back to e-commerce in a minute, but our customers outside of e-commerce, it's typically they have a number of different data sources that they need to blend and merge together. They have pretty complex workflows that they're integrating with. So it's kind of your traditional knowledge management use case, helping experts within the company know and understand and find their data, right? So the use cases there typically range from things like compliance, e-discovery, through to we do a fair bit in the life sciences where you're actually helping researchers within, say, for instance, pharmaceutical companies not only look at the space of literature around what they're researching, but actually the lower level content. So for instance, we've got some customers who actually are doing search over molecules, and then they're identifying what drug treatments are approved for those molecules. They're looking at similar molecules that maybe are under-researched. They're looking at the literature and joining all of that kind of core matching capability with a broader view of, who's funding what research in that area, what patents are out there, what adverse effects have been reported, what symptoms are these meant to treat. And so you kind of get this 360 view of the research space. Another great use case is exactly kind of that 360 view of looking at customers. So, for instance, this is on the public record. Red Hat has been using our capabilities around their support infrastructure, so that not only is it enabling better self-service by you being able to go in and say, "Oh, I found this Linux error. Let me go look that up on the Red Hat support portal," if you're a support customer, but their internal reps then are able to leverage that as well. And so those are kind of your typical knowledge management, lots of different data sources, fairly complex workflows, trying to kind of, encourage that serendipitous moment where people have, aha discovery moments, as well as just, straight up traditional search. More importantly, too, what we're often doing in that space is adding in machine learning and NLP and really trying to help the user understand what it is about this data that makes it interesting, and how can we layer some intelligence in there. E-commerce, I said I'd go back to real quick just to finish off that thread. That tends to be a lot more straightforward. Product catalog into the search engine, and then overlaying on top of that things like clicks and intent and various other signals, if you will, from the customer about what they're looking for. We also in our product, for instance, ship out of the box a recommendation engine, so you can drive what we like to think of as a multifaceted recommendation system, whereby you're matching based off of content, you're matching based off of the collective intelligence, the popularity, the clicks, etc. And then you're also personalizing and you're editorializing, according to what your business drivers are. And so by mixing and mashing all of those things together, you tend to have a much better result for your customer that not only meets what they're looking for, but also meets your goals in terms of revenue and margins and all of that kind of stuff.
And at the core of both search and machine learning is the idea of representing each entity as a numerical vector, whether that's product catalog or a bunch of Linux errors or molecules. In any event, you need numerical representations. You need like vector representations so that you can perform computations like cosine similarity. So I'm curious if when an enterprise typically comes to you, do they have a bunch of entities that are not in vector form, and you have to go through a process of vectorizing those entities?
Yeah, I mean, so most people come to us with some form of structured, or I hate the word structured versus unstructured. They come to us with things like Word documents, PDFs, etc., or they come to us with rows and columns in a database, or maybe they've got some JSON or CSV files. Really, you kind of name it. One of the things we try to do is be pretty forgiving in the types of data you're sending us, because we all live in reality. There's so many out there, this is one of the core things that Lucene at its very heart provides. And just for the listener's sake, if they're not familiar, Lucene at its core is a set of Java APIs that builds up what is called an inverted index. And then it provides a bunch of Java APIs on top of that, right? Solr then takes and churns Lucene, is essentially Lucene as a service, as well as adds in scaling, adds in fault tolerance, adds in things like faceting, and most of the things that require programming in Lucene are simply convention in Solr. And then Fusion builds on top of that by integrating Spark with Solr, as well as a number of other services and capabilities. So Lucene at its heart, what it's doing is very, very quickly, given some raw piece of text or tokens or strings or whatever you want to call them, Lucene has a process for extracting features out of those out of the original content, and then building up those vectors that you're talking about, and then very highly optimizing the data structures underneath the hood such that lookup and these search calculations, these query operations are all very, very fast and efficient, right? The inverted index that I mentioned, while people may not know that name right offhand, we're all familiar with it. It looks a lot like what is in the back of a book. So this word appears in this document at this position. Lucene is essentially doing that, and of course, it could do that across billions of books. Whereas obviously, a single index for a book is just that the page is in there.
Could you briefly discuss the process by which a search query is responded to with a ranking of the corresponding vectors that match most closely to that search? I know you've discussed this in several Software Engineering Radio podcasts, and I'll put those in the show notes, but I think for listeners who are unfamiliar with this, it's worth just discussing that ranking process a bit.
Yeah, well, so I'll try to simplify it because there's actually a number of different ways one can do it, and I won't go into all the gory details, but some models are probabilistic in nature, some are vector space in nature. So the vector space, since you alluded to cosine similarity, is the one I'll talk about here. So at indexing time, we come in and we build up this vector for the document, right? Essentially, the way Lucene's representing that underneath the hood is a sparse matrix. At query time, your query comes in and, it's a vector as well, right? It gets converted into a vector at query time, right? And so what we're doing is we take all of the terms in the query, and they can get quite complex. You can have phrases, you can have wildcards, you can have ands and ors and boosts and all of these different things, right? What Lucene then does is take that query. We go and what we have running in Lucene is what's called the term dictionary. That's essentially that back of the book thing that says, this term appears on this page. So Lucene breaks apart the query, very quickly goes and looks up what documents contain the terms that are in the query. Right, so you can see now we've got a match, and we know, document 5, document 7, and document 5000 all contain the word Bob, right? And document 3, document 5, and document 5000 contain the word Jane. And so then what it does is, so now it's got essentially a Boolean, set of results that need to be scored. So next thing it does is take those vectors and essentially do that cosine similarity between each of those vectors, right? And if you remember your high school math, the cosine of a vector or of an angle that is 0 is 1. And so if you think about that kind of logically speaking, right, if these two vectors in some n-dimensional space, if the angle between them is 0, then you would say, oh, well, not accounting for scaling of the length of the vector, this is, an exact match. So intuitively, I think that makes sense. And then, depending on the angle from there, you get a value between -1 and 1. Now, it's a lot more complicated in there because we do things like we can apply boost. You can apply boost to the query terms. You can apply boost to the documents. You can apply boost to the tokens. You have all these other weighting factors that you control. The nice thing is for most people using this, it just works out of the box, right? And you'll maybe tweak a few things here and there, but this really is the magic of how that ranking gets produced. What you then start to want to do is Solr, for instance, provides really easy places for you to plug in and say, oh, I want to use this value as part of my scoring. I want to boost by my inventory, for instance. So all else being equal between two products, I would rather show the one that I have more inventory on at the top. Or perhaps if I have information about how much money I make off of an item, like my margin information, I could say I want to boost the product that I have a higher margin on, because again, all else being equal, wouldn't you rather make more money than less? Why not, right? unless you think that other one truly is another match, a better match. And that's where, like I said, you get back to this mashing together all of these different features into a ranking, and you have really fine-grained control over that ranking if you want. Otherwise, for most people, they just kind of let it go. And just let it do what it knows how to do. And that's very different. That often takes a little bit of a leap for a lot of engineers who have been kind of traditionally trained on databases and relational logic, where you have a set and you're doing operations on the whole set.
Sure. So when you help enterprises implement search, I think you said you also help them implement machine learning solutions, kind of using the same platform, the same models. What is the relationship between search and machine learning? How are these two things complementary?
Yeah, that's an interesting question. And 5-10 years ago, I probably would have had a different answer than I do today, because the truth is today they're actually becoming quite blurred. Machine learning is getting integrated at a much deeper level. There's a whole movement that's called learning to rank, whereby instead of having a more rigid ranking model like a vector space or a probabilistic model, you actually let the ranking evolve based off of your user feedback. Now, even in that system, there's usually a baseline ranking that's provided by like a vector space model, but you can see that it's starting to get blurred more and more. And so that's really interesting at the low levels. But, to your point around your question, there are some higher layers here where, you might use something like a classification algorithm that takes in the user query and tries to classify that user's intent and says, oh, well, this person's asking about ping pong, whereas this person's asking about tennis when they, search for a racket. Right. And, the classifier would be bringing in lots of different information to make that decision. The query obviously being part of it, but maybe they know that, the ping pong user actually, all of their previous items in their cart, all of their past experience with the site has been all about ping pong, whereas the other one has been all about tennis. And so that classifier is really good at bringing together lots of these different features and saying, here's the intent of this, and then what the search system will do with that is take and shape the queries in such a way to return higher precision results for each of those users. So either more ping pong results or more tennis results. Now, the math for all of these things is a lot of times fairly similar. And in fact, like in my book, Taming Text, like we show how you can implement a classifier on a search engine. And we show how you can do some basic machine learning just off of using a search engine. And so, that's often a good enough solution. It's often an area, it's good enough for saying, hey, I'm going to go explore this more. It may not be the best in class as defined by, Google or some academics or, things like that, but it's often good enough for people. And there's a lot to be said for good enough when you're just starting to explore this or you're not sure if it's going to work or not. Other areas, I think, things like topic detection, where you're actually trying to identify what this content is about. All of those things often feed really nicely as metadata attributes on the content itself, which then can be leveraged by search for more precise search. It can be leveraged for doing things like faceting. For the readers or for the listeners here, faceting is essentially what you see on a lot of e-commerce sites when you go and search for TVs. And down the left-hand side, it'll say, hey, there's 13 Sonys, there's 27 Samsungs, et cetera. And you can click on each one of those and you're going to get a guaranteed set of results. And so machine learning often factors into those pieces. It's often also the building blocks for natural language processing, whereby you're trying to help the machine better understand actually, human either spoken or written text. And so you're parsing language, you're breaking it apart, you're trying to understand what that user is writing about a bit more. And so these are all very complementary capabilities.
We'd like to take a moment to thank our sponsor. DigitalOcean offers simple cloud infrastructure for developers. In one click, you can have a mean stack, a Rails application, an Ubuntu box, or another custom environment. Software Engineering Daily is proud to have DigitalOcean as a sponsor because DigitalOcean is the simplest cloud service provider. I've interviewed Moisey Aretsky, who is a founder of DigitalOcean, and he told me that DigitalOcean was based on this realization that other cloud service providers are so complicated. If you want things to be simple when you deploy your application, use DigitalOcean. To try DigitalOcean, go to digitalocean.com and enter promo code SEDaily. That promo code is one word, SEDaily. Now let's get back to our show. Could you differentiate between supervised learning and unsupervised machine learning?
Yeah, I mean, kind of as the name implies, unsupervised, the idea there is you as a human are not providing the computer with any hints as to what this content or what the task at hand is. So clustering is a classic unsupervised example. What you do, or an example, a lot of clustering algorithms are unsupervised, I should say. And so in those situations, what you're doing is you're giving, you take in your content and you say, here's a similarity function. And there again, there's that similarity function again, that ranking function. And you're applying it to all the content and you're grouping together all of those items that are closest together as defined by that similarity function or that distance. There's no human involved there. All you really have to do is just give it the data and it comes back with the results. You may have to do some tuning of the actual data you give it, but you don't actually have to annotate any of the data. Supervised learning, typically there, what you're actually doing is you have a training data set and a test data set. The training data set is you provide labels on it and say for this piece of data, here's the answer I know is the right answer for it. So in the classification use case where say you're taking in all the world's news and you want to label it with the type of news it is, it's sports, it's economics, it's politics, it's entertainment. You would take, and your training set would be a bunch of news articles with, labels on it: sports, entertainment, politics. And so you would feed that into your learning algorithm. Learning algorithm would look at the label and then look at the features and essentially is doing correlations between features and labels. And then you likewise at test time, you basically are withholding the labels and say, given just these features, can you predict the label? And so that's a supervised case because, we as people are giving, we're providing those labels. We're providing that initial set of answers.
Got it. On Software Engineering Daily, the topic of deep learning has come up a few times. Do you have any understanding behind deep learning? Can you tell me anything about that?
I've read a bit about it. It's not something I've done a lot. I haven't gone deep on deep learning yet at the moment, although I have explored some libraries out there that do deep learning. And my understanding is that we're essentially looking at really large neural networks where plus some advanced capabilities that integrate with them. The basic idea though is you remember in the supervised case we were talking about, there's actually a lot of work around those annotations, right? So I think the goal always has been with machine learning is the belief is that, hey, we would all prefer to have unsupervised learning because it's not as human intensive, but it's also really hard and really inaccurate. Deep learning, I think, is breaking down some of those barriers between the two, whereby you don't have to provide as much up front in terms of your data, in terms of saying this is what this data is about. And these large neural networks and such are able to analyze huge volumes of data and kind of figure out what should the labels actually be and what are the the correlations and things that are interesting. Again, like I said, I'm not an expert there yet, so it's on my radar for things I know I need to learn, and we actually have some. I've got some preliminary research going on there internally, and there's actually some really good open source out there too that people can get started with. But yeah, it's all the rage these days. And Google's been doing some really interesting thing, and Baidu and Facebook and the like. And so there's a lot of good stuff coming out of it. Typically requires a lot of data and requires a lot of hardware, from what I can tell.
Is it fair to say that there's an inverse relationship between how much data you have and how much supervision you have to do? Like if you have more data, is it fair to say that generally you'll be able to do less supervision? Like that kind of seems like the impression that I get from deep learning. Yeah,
I think that's kind of one of the premises of deep learning. I think a lot of data scientists will tell you too, even if they have a lot of data, some of their initial models and as they get towards production, you're typically dealing with smaller data sets, because it's often the case that there's a lot of redundant data in there. How many times do you like say you're building a recommendation system and you have 50 ratings of an item. Well, 51 ratings of that item doesn't add a whole lot of value. So but for these deep learning systems where you're looking at really complex relationships and things like that, I think the idea is take and apply a simpler model like a neural network, but give it way more data than we ever have before, and let it do its thing. But again, I'm not a deep expert there. I know the headlines, but not the practical side of it.
Same here. So you've done a lot of education in the world of information retrieval, just like in talks that you've given, and the software engineering radio episodes, and also in your book Taming Text. So when you teach people about the concepts of information retrieval, what are the things that people have trouble understanding?
Wow, that's a great question. There's I think a couple of answers. I hinted at earlier. I think a lot of people in college and university, they learn databases and they learn SQL and they learn relational logic, and they learn obviously Boolean logic, right? And so this notion of probabilities and this fuzziness, this notion that one day the answer might be this and the next day it might be another. I think intuitively we as humans get that, but we're not used to programming the machines to do that, and so that's often a stumbling block. There's also I can't tell you the number of times where people who once they get going on search, they just have this moment where they're like, oh, I get it. I remember one of our very first customers at LucidWorks. I went in the door and we were doing consulting for them. This is a pretty large provider of like power equipment, like generators and stuff like that. And the guy there was kind of this classically trained Oracle database guy, and he was building out their website, and their website was really heavily attributed because, as you can imagine, this kind of equipment has lots of attributes. Things around what how much power it needs, how much power it generates, like all of this fine-grained engineering, heavily refined information. Something like every document had something like 400 attributes. And he was trying to give their users a faceted view of that data. So again, going back to the facets of, hey, I know there's 5 of these and 3 of these, right? And he was trying to do this in the database, and it was this really huge and complex set of joins. And it took something like 5 minutes to run, which, just wasn't good. And so we came in and I was like, okay, well, there's this search thing and it does it out of the box. And he was like, no way. It's not going to do it. He's just totally doubting. And, within an hour, we had it up and running with basic faceting all in sub-second. And he was like, oh, okay. And then, fast forward, we did the implementation. They're all happy. I saw him a year later, and we kind of were joking about it. And he's like, yeah, I haven't touched my database in over a year. And this is a guy whose whole career was built on databases, and I've seen him several times since, and now his whole career is built on building these fuzzy systems whereby you're delivering this data in a much more interesting way because you can slice and dice it in so many different ways. And I think that's a really powerful aha moment. The other thing commonly with search and machine learning is, we as engineers, almost to a fault, we love to work on the fun pieces, right? And the quote unquote sexy pieces, right? Like the machine learning algorithms itself, or the core ranking function, right? But garbage in, garbage out still applies in this day and age. And what they don't realize is, when you're dealing with this multi-structured content, there's a whole lot of noise and there's a whole lot of garbage. Because let's face it, human language is tough, right? It's ambiguous, it's noisy, it's missing, it's all of these things, right? And so you often spend a lot of time on those things. Meanwhile, in the back of your head, you're wishing you were spending your time on this really cool neural network thing, right? I often talk about, in some of the talks I give, I talk about all the different characters that appear when you're doing text. There's jokers, there's evil villains, there's the class clowns, all of that kind of stuff. And if you think about human language, we have all of that, right? Like you get sarcasm, you get jokes, you get missing data, you get noise, you get ambiguity, and your job as a search engineer is to make sense of all of that.
Yeah, so you've talked about some different types of ambiguity. You've also mentioned fuzziness. And in one of your talks, you advocated embracing fuzziness. What do you mean by the fuzziness that we should embrace?
Yeah, I love that because like I said, it's often one of those mind-blowing things because I think a lot of engineers don't always think about statistics, right? I think this is why the data science movement has been growing so much, because you essentially have this next generation of engineers who are actually pretty good at math as well. And as soon as you start dealing with probabilities, you're dealing with if you think about writing tests, right? Well, like how do you write a test reliably to test something that has only has some probability of actually being the case? We're very used to writing tests that say, assert that this value is X. When in a search system, you might need to assert that this value is X or it's Y or it's Z, and it could be ranked in a number of different ways depending on what data you give it. And so not so much in the test environments, but once you get with live data, that's always the case, right? I often talk about a lot of our customers have what I call pet peeve queries. And the pet peeve queries usually stem from some engineer's boss coming and saying, "Oh, search is broken. I just did a query for X, and the answer I was looking for was way down the results set." And so then the engineer goes and tests X, and they sit and spend a lot of time trying to make sure that X is at the top of the result set. And so, by embracing that fuzziness, I think one of the things you're doing is you're thinking about the broader picture that, hey, yeah, this particular query may be broken, but the rest of the system actually works really well. It's just that one answer is not quite correct, and so then you ask yourself, well, how should I fix that one answer? I think the other side is you just get comfortable. You get more and more comfortable with looking at things in the light of ranking, right? And more and more data problems can be solved that way, and so you end up being a lot more successful by embracing this fuzziness, right? But nobody likes uncertainty, right? And so that's a hard thing to swallow as an engineer, especially as engineers. I think we pride ourselves in precision, right?
Yeah, makes sense. The Hadoop ecosystem has changed a lot since you started LucidWorks in 2008. How are the changes to the Hadoop ecosystem altering the way that people are architecting their big data systems, particularly with regard to search and machine learning?
Yeah, it's a great question. I mean, I think, back when we started, it was all just Hadoop and MapReduce. I mean, a lot of people don't know that Hadoop actually started as part of the Lucene project, and then
I didn't know that.
has spun out to become the thing that it is.
Was that when Doug Cutting was like, so he was just learning Java, and then he built Lucene, and then he just built Hadoop out of that?
Well, Lucene, was back in Doug started on Lucene back in '97.
Okay.
And then one of the Lucene projects was this project called Nutch, which is all about Doug and a couple of other people, Mike Caffarella and Andre Białecki and a few others, were trying to build this large-scale distributed crawler. And out came the game-changing Google MapReduce distributed file system paper, which Google essentially was using MapReduce to build Google's indexes. And Doug and Mike and a few others said, well, why don't we go implement that? And thus Hadoop was born as part of the Nutch project to build Lucene indexes in parallel, right? And then it's evolved quite a bit. Obviously, before Hadoop, it's not like building distributed parallel algorithms. That stuff all existed before too, right? I mean, there was things like the message passing interface. Heck, my first job out of college, I did parallel Fortran. So if you want to go way back in the archives, we could talk about that. And it actually had, some similar properties to MapReduce and that you would identify what areas of the algorithm you wanted to make parallel and what ones you had to, essentially do joins on or reduces on and things like that. I mean, it wasn't called that, but, very similar style. I think the both the blessing and the curse around this stuff is the blessing is, hey, people are keeping a lot more data and there's a lot more interesting things we can do with that. And there's a huge open source ecosystem for solving those problems. The curse, of course, of that is, information overload and trying to make sense of which ones are going to help me solve my problem. And, for us at LucidWorks, we primarily, look at a lot of those things as data sources, because, I don't think any of them are particularly good at the problems that we solve, namely that ranking problem. And so, for us, it's often about making sure that we can scale and keep up with that data. And I think the answer there is yes, we do. And then the other part of it is we do leverage things like Spark for doing our analysis of all of our user interactions, right? So in most search systems, you kind of have these two pieces. You have the real-time piece, which is all about answering the question at hand. And then you have this offline piece, which is all about, kind of whole collection analysis, log analysis, et cetera, where you're trying to figure out what are the patterns of interaction with your data, right? So, things like Spark, Storm, Pig, Hive, Hadoop, all of those things can help solve those. And, for us, we're pretty agnostic of it. We work with customers who have all of those things involved. The really interesting piece, I think, is, the Spark stuff is really interesting. There's Flink that's doing some interesting things too. Mahout does some interesting things on top of those projects. And so the machine learning and NLP pieces that built on top of big data are really interesting as well. And so for us, as I mentioned with the name Fusion, we kind of try to take the best in class and integrate it in with our applications, but then also give our users ability to plug in their own as well. But so yeah, it's a great time to be an engineer.
Do you find yourself at LucidWorks building out solutions for data science teams?
Yeah, I think they're always a part of the equation. I actually did a webinar. It's up on our website called Fusion for Data Science, where I walk through a number of different use cases and examples of where you can do interesting data science things in Fusion. I've also given a number of talks out there on using Solr, which is one of the core pieces of Fusion for data science. There's a lot of interesting things that search does for data scientists because, if you think about Yet one of the first things you typically do as a data scientist when you get new data is you need to kind of understand the size and shape and scope of it. And I think a search engine is a really powerful way of exploring that. And then along the way, you're obviously getting these vectors that you can go leverage as part of your machine learning. You can go and do things, like I said, of building these quick and dirty classifiers and clustering algorithms. We integrate with a lot of NLP tools and other things like that. So now you can start to, at the end of the day, kind of slice and dice that data in interesting ways. Our aggregations and signals framework, the faceting, the stat stuff, that's all built in. I think those also all fill in. And the cool thing I think that comes out of it is the stuff scales and just works, right? Solr's been around for a long time. It's really rock solid. It handles, billions and billions of documents, handles hundreds of thousands of queries per second, And so you can start as a data scientist with something at a small scale and be rest assured that it's going to be able to be maintained at very large scales by your operations. But as for building like a specific product that's just targeted to data scientists, that's not something we do. They typically are just they're involved alongside the engineers and the rest of the team in building out the application.
How do you think information retrieval is going to change in the next 5 to 10 years?
Oh, wow. I hate prediction questions, but
okay.
I'll take a crack, I guess.
Sure.
Because inevitably, people who try to, it's the classic one of the world will only need 6 computers, right? Or oh, hey, that Google thing, that'll never take off.
To put it more fluently, I mean, based on technological trends, where do you think the engineering side of things is going?
And that I feel more comfortable with. I mean, it's bigger, better, faster is the easy answer, right? But I think the voice is going to be really large, really huge. I mean, more and more applications. I think voice will be the interface. Right. And so that's going to drive NLP. That's going to drive the machine learning. That's going to drive search to be very deeply integrated with that. A lot of this learning stuff is going to be integrated in at deeper levels such that we have, like I said, those things around learning to rank, the classification and all of that, that you're able to better annotate and make more intelligent the data. You're able to better understand the user's questions. I think we are moving more and more towards an answer engine type model for interaction. I think the voice stuff is driving that. The mobile phone is driving that, right? Where we want the answer, not 10 blue links, right? So if you ask the question, hey, who's the president of the United States? You want back, the answer, not, a bunch of blue links that you then have to go click through and figure out who the president is. And so, we are at this, in this incredible golden age around not only having the information available to do interesting things with, but we actually have the compute horsepower more or less available. And so, I think there's going to be a sea change in engineering around, essentially ubiquitous computing. I think that's already starting to happen, right? I mean, you can go on Amazon or the like and push a button and have, 50, 100, 1,000 nodes at your fingertips, right? It's certainly very expensive, but you can have them. And if you think about, having what essentially amounts to infinite compute and infinite storage at your fingertips, what would you as an engineer build? What can you build, right? Obviously the laws of physics and all that still apply. I'm not trying to say we actually have infinite capabilities, but it's more than we've ever had, and it's so cheap. And so, in the next 5 to 6 years, I think that's really going to take hold.
What are the big voice technology? Because I feel like voice is it's getting really good, but it's still not quite there.
Yeah, well, challenge yourself here and take this interview, and you could go spin up, IBM has a speech to text part of their Watson product, right? and go run this interview through it and ask it to transcribe it, and you tell me the answer, right? I mean, they do a pretty good job, but they still need a human in the loop to fix the errors and provide feedback. But that's just it. Like, the computers are getting better and better at learning from their mistakes. So, that annotation cycle whereby we're correcting and giving feedback, is shrinking, right? So, it used to be everybody went off on Mechanical Turk and or something like that, a Crowdflower, and you would give it a bunch of unannotated information. Now what I think you tend to give is it's partially annotated, or it just needs to be corrected. There's this iteration loop between man and machine that is tightening that loop up and making it shorter, making it such that the human is much more effective at it, or has less to do, or can do more per minute or whatever it is, without it being as onerous as it used to be.
That's great. Well, to begin to close off, is there anything that you're working on right now that you'd like to mention, that you'd like our listeners to know about?
Well, without giving away too many things, I mean, I think we're really focused as a company on this question of importance, and this question of helping you identify what's important in your data. And so, a lot of our efforts are geared around taking the signals that the users of our product are giving us and learning from them, and then feeding that back into the search algorithms, feeding that back into other parts of the system, such that we can better predict what you're going to do, right? And I think that's what we're after in the application. I think that's what a lot of people are after when it comes to, especially consumer-facing websites, but also enterprise websites. And so, a lot of our focus is on those things internally, which, essentially amounts to machine learning and natural language processing. At the higher level, we continue to build out things like data connectors, scalable tools, et cetera. So we also, put a fair amount of engineering effort into those things. We have, I think a lot of the themes that we've talked about, without giving away too much, are on the table and being actively worked on by us. And so, if customers or listeners are interested in that kind of stuff, we certainly would be happy to chat with them and talk about their use cases.
Great. Well, Grant Ingersoll, thanks for coming on to Software Engineering Daily. It's been great talking to you.
Jeff, I appreciate the opportunity and look forward to talking to you again.